everyone, I'm solving Leetcode question 576, out of boundary passes. There is an m times n grid with a ball. The ball is initially at the position start row, start column. You are allowed to move the ball to one of the 4 adjacent cells in the grid, possibly out of the grid, crossing the grid boundary. You can apply at most max moves to the ball. Given the 5 integers m and max move, start row, start column, return the number of paths to move the ball out of the grid boundary. Since the answer can be very large, return it module 10 to the power of 9 plus 7. So let's take a look at the example. In the example 1, the starting position for this ball is at 0, 0, and then the grid says is m equals 2, n equals 2, so two rows and 2 columns. The maximum number of moves you can move is 2, so okay, if you move 1 time, you can move out the boundary 1 way, 2 way. If you move 2 times, you can move down first and move to the left to outside the boundary, or you can move down and then continue moving down to move outside the boundary. Or you can move to the right and then move up to move outside the boundary. Or you can move to the right and then move to the right to move outside the boundary. Since the maximum number of moves is 2, so you can move at most 2 times. So in this case, there are 6 different passes, so that's why the output is 6. So now let's look another example. In this case, we have 1 row and then 3 columns. The maximum number of moves is 3. Starting position is 0, 1, so it means it starts in the middle. So the output is 12. Why it is that time? Why it is 12? So let's take a look at the different scenarios. If the ball can move 1 time, can move up or move down in order to move outside the boundary. So that's 2 different moves. That's 2 different passes. Move 2 times. From here, you can move to the left, and then from the left, you can move in 3 different directions: up, left, down. So in that case, there are 3 different ways. Similarly, if you move to the right, you can also have 3 different passes to move outside the boundary. So in this case, if you move 2 times, you have totally 6 different ways. How about move 3 times? So to move 3 times, so move to the left, and then move back, and then move up. So that's 1 path. Move to the left, move back, and move down. That's another path. So there are 2 different passes. So similarly, so it's kind of symmetry here. So in this case, if you move to the right, move back, move up, or move to the right, move back, and move down. So 2 different passes. So 4 different passes for moving 3 times. So in total, sum all those up, you get 12 different ways. So 12 different passes in order to move outside the boundary within the maximum move limit. Okay, cool. So let's think about how to solve this problem. Okay, so one thing is we can move in 4 directions: up, down, left, and right. So that's the 4 different directions. So from the 4 different directions, let's say, going back to our example 1, from this position, so basically from here, so the let's say if we move here, let's say move up, and then in that case we already know that it's outside the boundary, and then even though the number of moves left, we can still do 1 more move, but since we already reached our goal, which means we move outside the boundary, so we got 1 pass. So what if in the second scenario, let's say I'm moving down here, I already used up 1 move, and then I want to, from here, I have 1 more move left at maximum, and then from here I have 2 different options. I can move down or move to the left. So it may not be very intuitive at very first glance, but let's say, okay, here, when the ball is at this position, it has 2 moves left, and then when it's moving down here, it has 1 move left. So at this position, the maximum move left is 1, and then this position has the corresponding coordinates as well. From here, we reduce the problem to, okay, starting from this position, and then you do maximum 1 move, because we have 1 move left in this case. okay, so how many different passes? So the number of passes is going down, going to the left. So reduce to the case that say move one time. So in that case, so we get our kind of like we kind of like break down the problem. Let's say for a ball that can move in all 4 different directions, and then what's the maximum passes? So let's say after we move the ball into the neighboring position, so what's the maximum passes starting from this position if we use this position as uh, a starting point? And then the maximum number of paths in the original position is equal to the sum of all the maximum paths from all the neighboring positions it can move to. So there are 4 adjacent neighbors the ball can move to if not constrained by the boundary. So that's kind of how we break down the problem. So it's actually another dynamic programming problem. So after discuss the idea for solving it, let's start coding. So basically so let's define, before thinking about caching or anything like that, let's just define the recursive case, the recursive function. So let's say ij and then the move. So basically the number of moves left. So starting from the position ij, let's say if I is less than 0, or I greater than equal to m, or j less than 0, or j greater than or equal to n. So that's kind of outside the boundary. So in that case, we just return let's say we just return 1. Okay. So let's say if we move outside the boundary. So in that case, that's kind of our base case. Let's say from here, when this ball is at the upper left corner and move left, and then it moves to a new position. In this position, the column, the index is outside the boundary, so there is only one path. So in that case, we return 1. What if, let's say, if the move is less than 0? So in that case, the number of moves, we cannot make any more moves. Let's say, okay, we finally reached this position, and we are about to move outside the boundary if we can make another move. But at this time, when we are reaching this position, let's say I equals 0, j equals 0, and we are at the upper left corner, the number of moves left is 0. So we do not have any more moves left. So in that case, we cannot do any more move. So in that case, we just return 0. There's no path. So after covering the edge case and base case, let's try to do the move. So up equals dfs I minus 1 j, and then move minus 1. So remember, we moved from ij to its neighbor, so that's why we reduced the move by 1. The number of moves left by 1. Down equals dfs I minus 1 j, sorry, my bad, I plus 1 j, move plus 1. Left equals dfs I j minus 1, move minus 1. Oh, I made a typo. It should be move minus 1. Right equals dfs I j plus 1, move minus 1. And then after we consider all the neighboring cells, we just return up plus down plus left plus right. So all the possible paths. Okay, so cool. In this case, we successfully code our recursive function. The thing is, it will probably run out of the memory or get the time limit exit error. So that's because utilizing this logic, we are still repeatedly calculating the values. Let's say, okay, so if we already reached this position, so let's say we start from this position and then we are doing the calculation. So we get one, okay, so starting in this position, we can move left and then move up with one move left. So that's two possible paths. And then let's say in another scenario, let's say our starting position is here, is in the row index uh, 1 and the column index 0, and then we have two moves left. And then from here we can move up, and then we go back to this position with one move left. So we reduce it to a scenario that we already encountered. And then here, if we do not store this value already calculated before, we just repeat it, calculate over and over again. And then this one could be in many different passes. Let's say starting from here, if my initial position is starting from here and I have two passes, two moves left, so I can also reduce to this case. So in that case, so let's just try to utilize another matrix to cache this one. However, here it's a little bit tricky. Usually in dynamic programming, we create another 2D matrix to capture, okay, ij. So basically, we record the previously calculated value, or we cache the previous calculated value at position ij. However, there is one more variable in this problem. It's the number of moves left. So here, so if you, let's say, if you moved into this direction, into this position, and then you have one move left, so you can move left and up. But what if you have two moves left, maximum two maximum moves left? So what if you already moved to this position, but you have three maximum moves left? So in that case, if you only have one move, maximum move left at this position, you can only have two options: move left, move up, to move outside boundary. But if you have two moves left, you can choose to maximum two moves left. You can choose to move to the left, move up, just utilize one move, or you can choose to move to the right and then move up and then right to move outside the boundary. So in that case, it's really depending on the number of maximum moves left. Then your number of passes will vary as well. So in that case, if we want to utilize previous strategy and create a matrix, we need to create a matrix not just for ij and also for the move. So that's kind of three-dimensional matrix. I just find it's a little bit hard to handle the previous matrix, the three-dimensional matrix. So what I'm going to do here is I'm just going to utilize the dictionary, and then with ij and move as the key. So in that case, let me check. So if it's outside boundary, returns 1. If it's move less than 0, returns 0. Or else, if ij move in this cache dictionary, I just return cache ij move. So I'm not going to calculate this one repeat and repeat repeatedly. So if it's already been calculated before, so it's not going to going down and traverse to check the neighbors and then doing the recursion if the value at this position with this number of maximum moves left has already been calculated. If not, so I just assign that, let's say cache ij move equals the sum, and then I just return the cache ij move. Yeah, so that's kind of how I utilize a dictionary to keep track of and store the values that I already calculated before, to avoid repeatedly calculating the same values over and over again. So after that, so I just call DFS. My I is my start row. My J is my end, my start column. And then my number of moves is the maximum move. Okay, cool. So let me just return this one. So just return this one. It says modular by this value, since it's too big. So modular by power capital plus 7. Yeah. So let me run the code. Okay, let me try to submit it. Okay, cool. So we get a working solution that passed all the test cases. So for this out of boundary passes. So let me try to go over the solution one more time. So let's say you basically the basic idea is to utilizing the dynamic programming. So we first consider the base cases or the edge cases. So base cases, if you move outside the boundary from the, let's say you moved from the previous position, and then right now you move outside the boundary from this position from the previous position, and to move here and move outside the boundary, you got one possible passes. So that's in that case you just return one. So we can illustrate this idea utilizing the example. Let's say if you are in your previous position, you are here and you are moving here. So the ij indicates the coordinates outside the boundary of this grid. So in that case, there is only one path. So let's say this one line here. So that's why you return one. What if you right now your move is less than or equal to 0? And then you are not yet outside the boundary yet. So because we already covered the input of the previous two line, if you are outside the boundary, you already returned. So here you're still within the boundary, but you have no more moves left. So you need to stop there. There is no more passes. So there is no path to move outside the boundary. So in that case, you just return 0. So after that, so we just check, okay, if this ij and move combination has been calculated before. If it's calculated before, we just store in the cache. So in that case, if it's calculated before, we just return the value that's already cached. If not, which means that's not being calculated before, so we check the neighbors. So we going up, going down, going left, and going right. Going up, we update the position. So this is the coordinates of the cell above current cell, r-1 and j. And then remember, we make one more move to its neighbor. So in that case, we reduce the number of maximum moves by 1. So we do the same for all the neighbors in the forward direction. And then in the end, so the total number of passes that will travel outside the boundary, the move outside the boundary, is just equals to, okay, from this starting position, equals to all the possible, all the passes from its neighbors. So here what this represent, okay, you start from position ij with this maximum number of moves equals move left, and then you are trying to move, your ball here is at this position ij right now, and you are trying to move it outside the boundary. So how many different passes? So in that case, you check the passes from its neighbors. So basically, it's equals to the sum of the passes. Let's say if you move this ball from your neighboring positions, so 4 neighboring cells. So that's kind of the recursion, or where the recursion comes. So in that case, we just return the value, the total number of passes. And then in the end, since this problem requires modular by 10 to the power of 9 plus 7, so that's kind of how we return. Let's say we run the function starting from our starting position indicated in the input, and then from there we can get the total number of out-boundary passes, and then we just modulo of the 10 to the power of 9 plus 7. So that's kind of our code and our submission. So that's the end of my video. If you like my problem, if you like my video, please don't forget to subscribe to my YouTube channel. That would help a lot. Thank you.